So there's one activation function which is kind of special in certain respects, and this is the so-called softmax activation function. Sometimes we have multiple output units, and we also have multiple output classes like positive, negative, neutral as the sentiment of some sentence, right? And in this case, we have maybe 3 output units for these 3 output classes, and we would like our output to represent a probability distribution over these classes. So this could mean like we have 3 units and unit 1 has activation of 60%, then that could mean this sentence has a probability of 60% to be positive, and it has a probability of 30% to be neutral, and a probability of 10% to be negative. So a probability distribution means that the outputs should sum to 1 and they should all be non-negative. And this is achieved by choosing the softmax activation function. The softmax activation function is defined as follows. We're in a layer, and the units, we have m units that are indexed by some index j that goes from 1 to m. And we have the pre-activations for each of these m units, right? Like we had previously, where for each output unit, or for each unit in the layer, we have a pre-activation. They range from Z1 to Zm. And what we apply on these pre-activations is the exponential function, and then we divide by the exponentiated set case of all other pre-activations, right? And in this way, we get yj. So again, we get the activation of a unit as a function of the pre-activation, but in this case, it's also a function of all the other pre-activations, and that's what makes the difference. Now, can we see that that really makes a probability distribution? So the question is yj greater equals 0 for all j, and does it hold that the yj sum to 1? Well, if you look at the exponential function where it maps the real line, it maps the real line to the positive real line, right? Or to the non-negative real line. Therefore, what's here in the enumerator is non-negative, or it's positive, and what is in the denominator is also non-negative. Therefore, yj is indeed greater or equal to 0, and that it sums to 1, you can verify yourself. In particular, you will have to verify that in one of the exercises. And also note in particular that softmax is a global activation functions, where all the other previously discussed were local. That means that the output of a softmax for unit j depends on the pre-activation of all other units, right? All the previous activation functions that we were looking at, they operated only on a single neuron, while softmax depends on the pre-activations of all the units in one layer, right? Therefore, softmax challenges the interpretation of individual neurons with individual activation functions. Instead, it supports a view of a function acting on a layer of several neurons. That means acting on a whole vector. And like to make that mathematically rigorous, let Z be the pre-activation in some layer. For a standard activation function, we have as activation, well, we apply our nonlinearity, such as leaky ReLU or sigmoid, independently on all the pre-activations, while for softmax, it is not independent. It is really each individual activation depends on all the other activations. Just take the case of, because it has to be a probability distribution, the higher one activation is, the lower all the others must be, right? So it's really a global activation function.